1, 2, 1, 2. Okay, yeah, thank you for the introduction and the invitation to speak here. Right, so green functions. I will first start out by telling you something about the background, then the state of knowledge about computing these functions, and then we come to the open problems and to computational and algorithmic methods. So let's see. So it's about groups of Lie type. So how do we get them? We fix a prime and a simple algebraic group over an algebraic closure of the field with p elements. So think of SLN, FP bar, or if you like E8 FP bar. These groups can be nicely constructed as shown by Chevalier already in the 1950s. You start out with a simple Lie algebra over the complex numbers, you take an integral form of it, and then you imitate some exponential construction, and you can really make these groups concretely. Now, working over this prime field means whenever we choose a prime power Q, then we get a finite group of rational points in this algebraic group, and in this way we get a finite group. So the order of these finite groups is roughly like this, Q to the dimension of G plus smaller powers of Q. So if we let now all powers, we fix the prime, but consider all powers of this prime, we get an infinite family of groups. So this is the whole setup of this theory, that you look at groups of the same type together, you collect them into infinite families, and you try to study these infinite families, of course, as uniformly as possible. So just the examples here, you could take SLNQ or the symplectic groups, or, which is interesting for us, which is always the big computational challenge, the exceptional type groups like E8 of Q. Now, what is interesting about putting these groups together into these families is that all groups in such a family have a common, what we always call combinatorial skeleton. There is a while group, there is a root system, which is the same for all groups in this family. So for example, for SLNQ, you always get the symmetric group Sn, whatever the Q is. For the symplectic groups, you always get the hyperoctahedral group. And for E8, you just get the while group of this order. So independently of P and Q. So the general aim in this whole subject is we want to study the irreducible representations of these groups. In this talk, I just look at ordinary characteristic zero characters. Of course, there are analogous problems in characteristic P modular representations, but here we just look at good old classical character theory. And of course, determining irreducible characters can have several meanings. You might want the whole character table, you might just want to have character degrees, values on certain elements, and so on. Of course, the ideal would be to find a uniform way to write down the character table in some way, but this seems to be the most challenging and out of reach at the moment. Yeah, and we want to do this, of course, in a uniform way for all groups in such a series. Now, how we do this today is we use this approach by Deligne and Lusztig, which was initiated in the 1970s, so it's already quite some time ago, but their fundamental idea was to use the French SGA theory of L-adic cohomology to construct representations in characteristic zero of these groups. Interesting for us here especially is, of course, there are the classical types, like SLN, symplectic groups, orthogonal groups. There you also have the N, which is running, yeah, the SLN, SPN. So usually there is also a certain combinatorial flavor coming to it. If you want to prove something about these groups, you can use inductive arguments and so on. But then there are these exceptional groups. And there you, in many cases, you really rely on computational methods. And E8 is really the most exceptional groups. And actually there's this nice survey article by Skip Garibaldi in the Bulletin of the AMS, which is called like this, E8, the most exceptional group, where he presents a whole spectrum of situations in which E8 shows up as Lie algebras in connection with the monster, whatever. Yeah? So it's a nice, nice read about the exceptional sense of this E8 group. And of course now, this is why I mentioned this with this combinatorial skeleton. This opens, of course, the possibility of using computer algebra systems in this business. Yeah? You typically have an infinite problem, but the skeleton is a finite thing, and so you can try to do something with computers there. Our system of choice is this Chevy project, which dates back already to the 1990s. Here are the various authors. This was originally developed in GAP3 and Maple, so we soon abandoned Maple because they change versions all the time and you don't want to rewrite your programs. GAP3 is coming a bit of age nowadays, so but Jean-Michel undertook the task to rewrite this for 64-bit machines, so you can still perfectly use GAP3 and the Chevy in it. And the latest development here in this respect is Jean-Michel started to write a port to this Julia language, which is a relatively new programming language. There's a big project in Germany funded by the DFG to create something like a computer algebra system around this Julia language, and there's already quite a bit of GAP ported to Julia, and maybe I say a bit more at the end of this talk. Okay, so this is the general thing. Now green functions. So I have to say at least a little bit how these functions come about. So in our algebraic group, we have a Borel subgroup. What Deligne and Lusztig defined is a partition of this flag variety, G mod B, into pieces indexed by the elements of the while group. I don't need to say the exact definition, but you have a partition into subvarieties, which they called X of W. Of course, they couldn't call them Deligne and Lusztig varieties, but nowadays they are called like this. And the point is that the finite group acts on these varieties. So by taking LRD cohomology, you linearize this action and you get representations over fields of characteristic 0. And this is what they did. And as you, I guess this is natural if you come from a background in algebraic topology, you have all these cohomology groups, Hi, for all integers I. So you take an alternating sum over all these things and take the traces of G on these spaces. Huh? Of course, there are theorems behind this. There are only finitely many spaces non-zero, they are finite dimensional, and so on. Like this, in any case, you define a virtual character of your finite group by a very complicated abstract method. And the problem is to compute explicitly these functions. So first of all, there's a little result here. If two elements in the while group are conjugate, then these two things are equal. So this led Lusztig to transform these things. So basically you transform these by the character table of the while group, so you get something which is indexed by the characters of the while group. And of course it's equivalent, knowing one is equivalent to knowing the others. These were called almost characters by Lusztig. For example, these are already orthogonal functions of norm 1, but in general they are not virtual characters anymore. Of course, now these are only as many functions on your finite group as you have characters of W. Huh? Your finite group, GFQ, I mean, if Q grows, everything gets larger and larger. This is just a finite, tiny little chunk there. So one might wonder how much information does this give in the end. And there's this remark of Lusztig in his book from 1984, which I think is not so well known because it's just a little remark at the end of the introduction. He didn't even bother to write this as a theorem, but it says the following. Actually, it tells you quite a lot about the character table if you just know these RWs or R5s. Namely, you get something like the average character table of your group. So what is meant by this? So take a conjugacy class in the algebraic group, which is defined over FQ. Then if you take points here, if you take the points in FQ in this class, it will fall into finitely many classes in the finite group. And what you could do, firstly, is just take the average value over these representatives of the finite group. Huh? This would be somehow the naive thing. What Lusztig says, you take a somewhat more clever average value, namely you take this here. You give weights in this to this sum, where these AIs, this is also a typical thing in this whole theory, you take a centralizer of an element in the algebraic group, it need not be connected, you mod out the connected component, this is always a finite group, and you give just this as, so it's something like a clever average value, but in essence it's just the average value over a class in the algebraic group. And all these you can compute in the form of an algorithm once you know just this finite little chunk, these are phi's of the whole space of class functions on GF. Huh? Quite an amazing statement. As I said, it's just a little remark in the introduction of Lusztig's book. Yeah? Okay, so this just to say that it's really, if you are interested in computing the irreducible characters of these finite groups, the first and essential thing is to get these RWs or R5s. Okay, so the green functions are just a small piece of these R5s, namely you only look at unipotent elements of your group and you restrict this RW just to the set of unipotent elements. So it's even a smaller piece from the whole set of character values. And this is what you call a green function. And we also call these transformed things, also call them green functions. Huh? So it's just a restriction of this R phi to the set of unipotent elements. Huh? Well, this is not important for this talk, but I should just mention it. Of course, by their construction, all these things have values in QL bar, because these constructions come from this LRD cohomology constructions. But actually, these things have integer values, so you don't have to bother about this QL bar, really, or embedding it into complex numbers or such things. Then there's a character formula, already proved by Deligne and Lusztig, which shows that if you want to compute all values of these R phi's on all elements of your group, it's enough to know them on unipotent elements plus some inductive procedure. Huh? So what we really need is to compute these green functions. So just now to fix things. So we have the irreducible characters of the while group. Let's say there are m of them. And let's say n is the number of unipotent classes in your finite group. Then the values of these q phi are given by an m cross n, m times n table. Yeah? Rows indexed by the irreducible characters, columns by the unipotent classes. Now, of course, the m, number of irreducible characters of W, doesn't depend on anything, just on the group. And the n, the number of unipotent classes, only depends on the group and the characteristic we are in, but not on the actual power of Q. Huh? For example, so let's just point it out. So for each Dynkin type, that means for each type of group and a prime, we want to compute this finite table of green functions of size m times n. Yeah? For each type of group, we have this problem. The size is fixed, but of course the values depend on which power of p you take in the end. Huh? So example, E8, there are 112 irreducible characters of W, and the number of unipotent classes depends on the characteristic. In characteristic 2 you have this many and so on, and as soon as p is big enough, it becomes stable. This is a typical thing for all groups. As soon as p is big enough, things become stable. And this was computed by Mizuno in this absolutely impressive paper from 1980, where he computed explicitly the unipotent classes of groups of type E8. Okay. Now, what is known about the values of these green functions? So this is the slogan here. Yeah, they are almost known, by a general purely combinatorial algorithm. So I have to explain a bit what I mean by this. So first of all, if you look at the values of these functions and you organize this table of values nicely, it has some kind of block triangular shape. And this is more precisely, it's the following. So you fix a phi, you have this function q phi, then there's a unique unipotent class such that the support of this function lies in the Zariski closure of this class, and if you restrict to this class, it's non-zero. This uniquely determines this class. So actually, you get, well, if you take this as a definition, which is not the original definition, but for the purposes of this talk, we can take it like this. So you can associate to each phi a unipotent class. Yeah? Then we define this number, which by general properties is always an integer 0 or positive. And we define these y functions, which is just the restriction. Is there a pointer here or? Yeah, so I said R, the g phi is non-zero in this class, so we take the restriction and define just this function here, but rescaled by this power here. Yeah? And then there's this big theorem which really took, first versions of it were already available quite early in the theory, but with restrictions on p and q, the characteristic had to be large, the power of the prime had to be large, and so on. And to get rid of all these conditions, this was finally achieved by a paper by Lusztig in 2012. So we can state it now without any condition. It works in all p, q for all groups. Huh? So you can express the q phi as linear combinations of these function y phis, and you have these coefficients there simply. And this matrix then of coefficients is some kind of triangular matrix with ones on the diagonal. This is why we did this normalization. If we hadn't done this normalization, we would have this power here on the diagonal. And this can be computed by a really purely combinatorial algorithms. Yeah? Once you know, well, here I defined this map by this property, but actually this map is known in advance. For the experts, this is just the Springer correspondence, which had been determined independently of the theory of green functions. And this is implemented, for example, in Jean-Michel's 64-bit version, already in the old version, and it's just a function ICC table. You give as input a group, a prime, and it spits out this matrix of these p's there. So this is just an algorithm which relies on the knowledge of the Springer correspondence, which is available by tables for the exceptional groups or combinatorial algorithms for classical groups. So of course all these things are included in the Chevy system, and then you write a little algorithm which has to solve a matrix problem, and you get out this matrix. Yeah? So this is already a huge part of the computation of green functions. Yeah? You express them in terms of these y functions. So now I can explain what this almost known means. So the rest, which remains to be determined, are of course these y functions. Yeah? So let's fix phi. We have the corresponding unipotent class and this little y function on it. To get the values of this y, that means the restriction of q phi to this class, we have to choose a representative in this class. And again, knowledge of the Springer correspondence. And this almost determines this function. It determines this up to a sign. Huh? So there, given phi, there is a sign such that up to this sign, I know the values of this y function. So the whole problem of computing the green functions is reduced to computing for each irreducible character of the while group a sign. Yeah, this is already a fantastic achievement. Yeah? If you start from the definition, you have something, these green functions defined by LRD cohomology, where a priori there is no way how to compute this, but this whole machinery leads to a problem where you just have to, for E8, you have to determine for each prime 112 signs, huh? One for each irreducible character of W. And of course, as I said, this theory exists since middle of the 1970s. There has been a lot of work on this. For example, Shoji, in several articles, the last of which in 2007, where he dealt with classical groups in characteristic 2, which is always a troublemaker for classical groups, he determined all these signs. For exceptional type, already Benyon-Spaltenstein did actual computer calculations back then, what ICC table of Jean-Michel does now in 10 seconds for E8. I don't want to know how long the computers were running back then, but they could only handle primes which were not too small. For example, for E8, this means good primes, so except for 2, 3, and 5. And of course, for groups of small rank, which are small enough that you can even compute the whole character table or large parts of it, of course, this includes then, you can read off the green functions from there. So this includes G2, the paper of Chang and Ri already, and others, 3D4, F4. Yeah, for these, I just mentioned some names here which have contributed to this work. So if you look at all these previous works, then what remains to be done? Classical groups are done, and there are a few cases in the exceptional groups. Namely, the open cases are twisted E6 in characteristic 3, E7, characteristic T2 and 3, and E8 in 2, 3, 5. These were the open cases. Now, how to deal with these cases? So how did, for example, Malle work out green functions for E6 and F4 in characteristic 2? Well, he explicitly used an inductive approach. You try to get as much information about character tables of large parabolic subgroups. You induce, use all kinds of relations, and hope you get enough relations up there, which determines in the end everything. So, but for this, you have to induce class functions from parabolic subgroups to the whole group. They did this for F4, E6, but do you want to do this for E8? You have to find class fusions from parabolic subgroups in E8. Maybe it's possible, but this is first of all tedious technical work and really boring and nasty work. It would be much nicer to have more elegant methods. And this is why up to nobody, in principle, of course, you could solve these problems there, but nobody did it up to now. And there is now a theoretical result which helps here, which I proved last year. So what I showed essentially is, so let's look at such a green function of the finite group over FQ. So there we need to determine this sign. And this theorem says you can compute this sign from the sign for the base case where you look at your group over the prime field. Yeah? So this is again a big reduction of the problem to a much smaller number of cases you have to look. So first of all, this had a theoretical consequence that I will not speak about here, but maybe on the workshop in May. So it has to do with the Glauberman correspondence, but for our problem here it means I only have to look at this base case where f is equal to 1. So in the end we don't have these 5 infinite families that we have to solve, but we only have to compute the green functions for these 6 individual groups. Yeah? Of course we want to do this for E8 in the end. E8 has 112 such functions. So if we knew the character table of E8 of 2, like for other groups in the atlas, then of course you can do some backwards engineering and you easily get the green functions and the sign. For example, this one could do nowadays the character table of F4 of 2, E6 of 2 is in the atlas. One can easily recover the results of Malle from that now, just by back reading. But can you do this for E8? So Frank Lübeck, he has these fantastic programs on his webpage where you can try at least to find the number of conjugacy classes. So the character table of E8 of 2 would have only, this is incredible, no? only 1156 conjugacy classes, but of course the group is enormous. The character degrees, the classes will be without any bounds. So you cannot compute the character table even with the best computers in the world nowadays, I guess. So you need something else to get a hand on these 6 individual cases here. So when I started this project, of course I was trying several things there, but since after all it's just 6 individual groups, it must be possible to do something there. But what do you have to do to get the solution? And so let's just recall this. We just need to find these signs in the end. And there's one additional relation which did the trick finally, namely if we sum all these R phi's that we want to compute over all irreducible characters, then this sum is just the permutation character of our finite group on the cosets of this Borel subgroup. So this is a relation at least. If we can manage to compute this, then maybe we get some conditions here which help us. This sounds first a bit unlikely, but in the end it does the trick. So let's, so this is one technical page. I have to say what information you get. So let's start again. So the green function is the restriction of this R phi to the unipotent elements. We said ICC table function. You can write these Q phi on the unipotent elements as linear combinations of these Y functions. Yeah? With these coefficients that you can determine purely combinatorial algorithms. So now we take this sum, of which we know it's the value of the permutation characters. We put in the formula from above, so we get a double sum over phi prime. It's this one. I rearranged the 2 sums, so you get this. And here the middle term, all this is known from the Lusztig-Shoji algorithm. So let's call this coefficient simply p phi tilde here. This is just this here. So we write this whole sum just as a sum of Y functions. Now fix a class, a unipotent class C, and a representative. Then I said the Y function is almost known up to a sign. So we write this value as a sign times something which is known. This is what I said there, almost known. So we put this into this formula, we evaluate on U. So we get this here evaluated on U. Now, since U is in C and the Y functions only have non-zero values on the C, I can restrict this sum to all phi prime which belong to this class. So this. Then this here is this. So we get this. Yeah? All the ingredients are not so important, but the important is a linear combination of these signs with something which is known. And this is the value of the permutation character. And the permutation character is just count all cosets such that G inverse UG is again in here. So essence of this computation is if we can compute the right-hand side, then we have here on the left-hand side a linear combination of some signs, and we can hope that this linear combination is strong enough to tell us something about the signs. This is okay, huh? Okay, so let's look at an example. E8. Let's take prime not equal to 3, so the interesting cases for us will be 2 and 5, because the others were done by Benjamin Spartenstein. So there is a unipotent class which is called E8 of B6 with the representative Z77, lemma 59 or something in Mizuno's paper. So this class is characterized by the fact that this little component group is a symmetric group S3, and the centralizer order of this element is 6 to the Q28. Now, there are 3 phi which map to this class here, and they are, well, depending on how you label irreducible characters of Weil groups, so this is Spaltenstein's notation, so this means is a character of the degree 2240 with some index to identify it. Here's a character of degree 175 and 840. And we want to determine the 3 signs. Okay, the Springer correspondence It was known by Spaltenstein before. Yeah? So we know that these are these three characters. And we want to determine these three signs. Benyon Spaltenstein did this already. They found if p is bigger than 5, then the first two signs are 1. And this is why this is an interesting class. Here the sign depends on the congruence class of Q mod 3. So sometimes it's 1, sometimes it's minus 1. This was the only known case where this sign could ever be minus 1. This is why I chose this class as an example. In all other cases, these signs are always 1. What was known up to now. Yeah? Okay, so now we take P2 and 5 and we run Jean-Michel's ICC table. We get the following value of this permutation character on the, I mean, we can express the permutation character on the one hand as a linear combination of something known with the signs, and on the other hand, it should be the permutation character. The linear combination is this. Here's a coefficient, a sign, here's a coefficient, this sign, here's a coefficient, this sign. And this should be equal to this. Now, my theorem that I mentioned, I don't need to look at any q, I just need to look at q equals p. So we just have two cases, p equals 2 and p equals 5. So if p equals 2, you get this identity. Permutation character has to be this linear combination of signs. For p equals 5, numbers get a little bit bigger, but you again have this identity. And you see, from these identities, you can already determine one signs. Do you see this? Yeah? Since the left-hand side, after all, we are counting something, so it has to be an integer which is not negative, so that this sum here is always positive. This sign must be 1, just because of the numbers. And the same here. Just because of the numbers, the only possibility is this is 1. Yeah? Just from this. But what about the two others? Now, for this, we should compute this permutation character. But look at the numbers here. This permutation module is roughly of the size square root of the group order. So this is still out of the question to create this permutation representation. But at least, using the Brucher decomposition, you have at least, you can make an iterator, speaking in terms of programming languages. You have a way of running through all coset representatives in a systematic way, namely each such double coset contains exactly this number, where this is the length of W cosets. So you start with W1 and increase the length, and you can enumerate them. At least in principle, you can write an iterator to do this. Now, in the paper that I wrote, which just appeared in the articles in press in Journal of Algebra, and it's for the special volume for Chi as well. So I looked at the case p equal 2, and I didn't take Mizuno's Z77, but there's another representative in this class which he calls Z78, because there's a slightly simpler relation. The other prime, the other sign doesn't occur in there. You just get this identity. And so how can you do this now on a computer? Suppose we want to show again that this sign is -1, like in the Benyon-Spaltenstein case. So we do this by contradiction, assume it's 1. Then, well, if we put 1 here, we get a minus, so the number of cosets should be this. Now, this was last year when I wrote this article in April, May, I think. So I just used Chevalet's construction to create this Chevalet group, E8 of 2, so it's in a 248 dimensional representation. I write my iterator there for the cosets, and I just start to compute with matrices and so on, and try to find cosets which are fixed by this element. And actually, I start to run through elements of small lengths. At some point, I find strictly more than this number, so contradiction, the sign must be 1. So you see, from the nature of these equations, sometimes you don't need the exact number, you just need a bound, a lower bound for the number of cosets. So you need it to go up to lengths of 24. by looking at actions of while group elements on roots, some technical things, you can discard a certain number of while groups element beforehand, before doing any computations. But anyway, but the nasty thing was, yeah. Of course, I didn't sit there one year. You can easily make this a parallel program, huh? Since you can run this program for each W and use your iterator to run through the cosets. So, and even in my university in Stuttgart, I could easily find some 5, 6 computers which have nowadays 6 kernels, whatever, and the programs don't need much memory. They just need time. Huh? And so I had 30 or 40 processors, so what takes 1 year was done in 2 weeks. Huh? But of course, this was not really satisfactory. I had a working program, but it had its limitations. For example, with this Mizuno Z77, this was just completely out of the way to compute this. Huh? But at least in this open paper, paper, we could handle all cases in type E6, E7, which were open. Huh? Here, everything is much smaller, the numbers are smaller, and so you don't need a year, maybe you need a week, and it works out. Huh? So this was fine enough. But then the challenge remained E8. Huh? So we had to do something about the programs here to get rid of this year here. And this was for p equal 2. So if we do p equal 5, yeah, this would, no way. Huh? Okay, so there then we use this Julia programming language. And there's also well, it has various interfaces to gap, singular, and so on. So if you don't know this Julia, what characterizes it? It's a nice programming language like Python or Gap or any such system, but it has some way of compiling just in time. So if you respect a few tricks on how to write your programs, then you can get speed close to C programs. Huh? But programming as such is as easy as in Python or in Gap. So that's a very nice thing. Now, first of all, so from this point on, many things were also done in discussions with Frank Lübeck. So first of all, he said, don't work with your 248 matrices, but just work with words in the generators and Chevallier's commutator relations, because then to sort out a word, bring it in normal form, you just have list handling and not matrix multiplication. Yeah? Okay, that's one thing. And secondly, you can use another trick, namely, instead of doing all these computations with the Chevalier relations for all elements in your finite fields millions of times individually, just replace the t's in these generators by indeterminants. First do a generic computation over polynomial ring. Of course, this is a big polynomial ring in as many indeterminants as you have roots in your root system. But nowadays, arithmetic in polynomial rings in these systems is good enough to do such things. And then, of course, to go down to your finite group, you have to, well, you get some polynomial conditions for your cosets to be fixed, and then you have to you have to go down to your finite field again. So you have a bunch of polynomials, and you have to count solutions over the prime field. Huh? And this is, of course, a very hard problem. Huh? If you have n indeterminants, well, you cannot run through all the p to the n possibilities. Huh? You have to do something else there. So one observation which comes out, because these Chevalier commutator relations, they don't produce arbitrary polynomials. There's some nice structure to it. So there are many variables can be eliminated. This means if you look at the polynomials, many polynomials have the form. There's some big combination of terms involving many variables, and then maybe plus x59, plus one single variable. And of course, all such variables you can eliminate and make your system smaller. Yeah? And surprisingly, there are many, many such cases, and there are even more if you first run a Grödner basis algorithm on your system of polynomials, it will produce even more linear terms. And if you choose the correct term order, then this really goes in 0, nichts, as we say in German. Huh? So we do this. And so I implemented all this in the Julia packet. Frank has independent programs in GAP, and I think it's also good that we don't tell each other all details of everything, so that we have two independent verifications of these programs. But the results are as follows. So let's go back to E8. This was the number we had there. For p equal 2, this permutation character value should be equal to this thing with these two signs. And now with this new programs, be it my Julia package or Frank's GAP programs, we don't just get lower bounds, but we can even compute the exact number, which is this, and it takes less than 2 minutes. And so if this number here is this, then you can deduce what the signs are. Namely, one must be 1 and the other -1. So really these relations are strong enough to determine these signs. For p equals 5, this was the number you should get. And you see this is already bigger, but again, so the program counts this number of cosets fixed by Chevalier commutator relations, all discounting points over finite fields in less than 4 minutes. And if just by comparison, the total index of here is this number. So you find this tiny little number of cosets which give the number, the value of the permutation character there. So again, if this is the value which this should take, you get this. It determines the signs. These are just these two examples, but these now really make us confident that we don't have to wait for years and years to compute this project, but we will be able to determine the green functions for E8. There's, of course, a lot of technical work to do. You have to go to Mizuno's paper, type in the representatives. You do first 5 mistakes when you do this. You have to check 10,000 times that everything is correct, but you really have an algorithm now to do this. We haven't done it yet completely, so I cannot write a theorem now, but I think this shows this can now be managed. One issue that I want to mention also here is, if you work with, for example, Mizuno's paper, this issue is only in characteristic not 2, of course. How do you construct these Chevalier groups? The classical construction is you take your simple Lie algebra, you have to make it integral. For this you have to choose a Chevalier basis, and these Chevalier bases are only unique up to choosing some signs. There is no way around. The way it was done is there's this thing with this, you have to choose extra special pairs of roots and this and that, and then you have a system of signs. And of course this raises a problem. Now I write my programs which make a choice. Frank writes his program which make a choice of Chevalier basis. Mizuno has in the last page a tiny little way you need a loupe to find the entries. He has a table there where he fixes the signs. And of course these signs are not all the same. You have to, if you say I want to use Mizuno's representative, which says x alpha of 1 plus x alpha plus -1, there's an issue there. So what I want to promote here is this issue. There's a canonical solution to it. There's no it's not arbitrary about this Chevalier basis, but based on this work of Lusztig and this article that I wrote, there's a canonical choice, and I would like to advertise using in the future this canonical choice so that one can make unique references. I say I use these canonical things, and then I don't have to work back and forth between various choices of Chevalier basis. Okay, so this is this, and then just the next steps. As I said already, we now think we will be able to compute this whole project. And then, of course, They are not just the ordinary green functions, but they are generalized green functions. They are more complicated, even more complicated, but this is the next step, what has to be attacked. There hasn't been really as much work on them as for the ordinary ones. And then, of course, in the end, we want to have complete character tables of these groups here, not just average character values, but actual character values. And of course, we hope that, and this is the last remark, Jean has started to rewrite GAP also in Julia, so that in the end, maybe there's a whole big package in Julia which can all these things together, singular, GAP, this, that, and so on. And with this, I close. Thank you.